Hello, everybody. I hope you're doing well. Welcome back to another video in our probability and statistics playlist. So what did we do in the past video? So in the past video, we have established that the problem we're trying to solve is proving that the sample variance is an unbiased estimator, right? And these are the four givens. Recall, right? We recall that x sub 1, x sub 2, x sub 3, all the way to x sub n are independent random variables. The population is mean of mu and variance is sigma squared. So you are sampling from this population, which is having a mean of mu and a variance is sigma squared. We've also established a basic intuition as to why the expectation associated with the random variable x sub I is equal to mu and the associated variance is sigma squared. And we've also introduced, from our previous video that the sample's variance is 1 over n minus 1 times the summation from I equals 1 to n of x sub I minus x bar squared, and we recalled some helpful properties of expectation. So now we have everything we need to carry out the proof. So what are we trying to prove? So remember, we're trying to prove that the sample variance is an unbiased estimator. But let's go back to the definition of an unbiased estimator. Well, it means that the expectation associated with the sample variance is equal to sigma squared, right? Your estimator is actually tending toward the population parameter. So we have this equality we're trying to show. And that's equivalent of saying the expectation associated with 1 over n minus 1 times the summation from I equals 1 to n of x sub I minus x bar squared equals sigma squared. So this is what we're trying to do. So we see off the bat, right, that n is a constant. N represents our sample size. So we know 1 over n minus 1 is a constant. And we also see that we have this summation right here, and it's of x sub I minus x bar whole squared. And we're taking that over summation. I think what might be a good first step is to expand this binomial out right here. So what does this give us? Well, this will be the expectation of 1 over n minus 1 times the summation from I equals 1 to n of x sub I squared minus 2x sub I x bar plus x bar squared. And recall in our property summation, right, we have this summation here of these three terms. So we can kind of split the summation over the individual terms and solve each problem independently. So this is going to be equal to the expectation of 1 over n minus 1 times the summation from I equals 1 to n of x sub I squared. We're going to close this right here in parentheses. Minus summation from I equals 1 to n of 2x sub I x bar plus summation from I equals 1 to n of x bar squared. Okay, so now we have this summation here broken up into individual terms. Okay, so we're going to proceed through each of these problems, each of these terms independently. Let's start with this third term since this is the most straightforward. So we see that x bar here is just a constant, right? It's just the sample mean and it's just one number, right? So if x bar is a constant, then x bar squared would also be a constant, right? And we're taking the summation from I equals 1 to n of a constant. So this term is just equivalent to adding x bar squared n times. So the summation of this term is just going to be n x bar squared. Likewise, in this middle term here, we see that the 2 and the x bar are constants. So we can pull them out of the summation because the 2 and the x bar don't depend on the index I. Unfortunately here, we can't really do anything on this term right here, the x sub I squared, as x sub I is dependent on index, but we're going to get to this later. There's a special way we need to handle that. So let's actually start. So let's actually write out what we have. So we have the expectation of 1 over n minus 1, summation I equals 1 to n of x sub I squared, minus 2x bar, summation I equals 1 to n of x sub I, plus n x bar squared. Okay, cool. So now we've handled these two terms, right? Now what else do we notice, right? We notice here that with expectations and the fact that you're taking the expectation of sum, we can invoke property 1 and basically separate out all these terms right here, right? And we also know that 1 over n minus 1 is just a constant multiplier. So what we can do with the expectation, I didn't write it out, but you can see my previous videos, that since 1 over n minus 1 is a constant, we can pull it out of we can essentially pull it out of the expectation. So we can make our lives easier by invoking the constant multiplier property of expectation and the fact and property 1. So we'll have 1 over n minus 1 times the expectation of summation I equals 1 to n of x sub I squared minus the expectation of 2x bar summation I equals 1 to n of x sub I plus the expectation of n x bar squared. Okay, cool. So now we have this, right? So let's look at this first term here, right? We see that we're taking an expectation of this summation, right? But what is this summation right here? It's just x sub 1 squared plus x sub 2 squared all the way to x sub n squared. So we can again invoke property 1, and this term is simply equivalent to the summation from I equals 1 to n of expectation of x sub I squared. In the second term, we can do something even clever, right? What do you know? What is this term here doing? The summation from I equals 1 to n of x sub I. Well, that's just simply adding up all the x's, right? But wait a minute. If we're adding up all these x's, right? Isn't that just simply the sample mean times n? Well, that's where we're going to make a clever substitution here. We're going to replace this summation here from I equals 1 to n of x sub I with nx bar. So you have this term right here simplifies to this. This second term is going to be expectation of 2x bar times nx bar, right? Remember the definition of sample mean. It's just simply adding up all the numbers dividing by n. So this part here is the adding up all the numbers part. So that's what this term is. And then we have this expectation of nx bar squared. So what we're going to do is, we are going to pull out this n here. So we'll have n expectation of x bar squared. Okay, so now you have this 1 over n minus 1. Okay, great. So what does that leave us? Well, we have to figure out what is this expectation of x sub I, like squared, right? Sorry, I meant to put a parenthesis here. So it's expectation of x sub I squared, right? So let's take a look at this variant. Let's take a look at property 2. So I'm going to change my color to yellow. And we have that the variance of x sub I is equal to the expectation of x sub I squared minus the expectation of x sub I whole squared. So we know that the variance of x sub I by our assumption is sigma squared, and we know that the expectation of x sub I is mu. So we know that the expectation of x sub I squared is sigma squared plus mu squared. So that's helpful. So change our color back to red. So this is going to be 1 over n minus 1 times summation from I equals 1 to n of sigma squared plus mu squared. And then we're going to handle these two terms in an interesting way, right? So remember how we said that the expectation of x plus y is the expectation of x plus the expectation of y? Well, this equality, right, applies both directions, right? So this is just simply going to be the expectation of, 2n x bar squared plus n x bar squared, right? So combining like terms, this is just going to be plus, or this is actually going to be the minus expectation of n x bar squared, right? We're just essentially using, property 1 in the reverse direction. Okay, cool. So let's figure out what the summation is. So this is just going to be 1 over n minus 1, and this is going to be n sigma squared plus n mu squared. And we still have to figure out what is this value here, right? Expectation of n x bar squared. So we'll pull out an n because we don't have to worry about that. So all we have to do is just figure out what is this x bar squared term doing here, right? And one thing we can do is, as you might have guessed, invoke property 2. So let's change our color to yellow. So we have that the variance of x bar is the expectation of x bar squared minus the expectation of x bar whole squared. So what is the variance of x bar? So think about x bar as just x sub 1 plus x sub 2 all the way to x sub n, right? Over n. So in this variance, right, you have a 1 over n multiplying by the x sub 1 plus x sub 2 all the way to x sub n summation. So we know that the variance of, a constant multiplier times x is simply going to be c squared times var of x, right? And how can you understand this intuitively? Well, imagine you have the data as at 1, 2, 3, 4, 5, and you take the sample variance according to this formula right here, number 4, right? Well, imagine doubling that data, right? So you have 2, 4, 6, 8, 10. So these x sub i's will be multiplied by 2, and the x bar here will be multiplied by 2. So you'll have a 2x sub I minus a 2x bar, but you're squaring that, right? So that's essentially meaning that each of the terms in the summation is getting multiplied by 4. So your variance actually quadruples when you double your data. So just like that, you will have 1 over n whole squared times the variance of x sub 1 plus all the way to x sub n. And use our given that the variance of x sub I is sigma squared. So you'll have 1 over n whole squared times n sigma squared, right? So this is just going to be sigma squared over n, right? You can go through the algebra yourself to verify that, right? And the last thing we have to figure out is what is the expectation associated with x bar? Well, what is x bar, right? It's just x sub 1 plus x sub 2 all the way to x sub n over n. And you know the expectation of x sub I is mu, right? So you can pull out the 1 over n, right? And then when you sum expectation of x sub 1 plus expectation of x sub 2 all the way to expectation of x sub n, it's just mu n, right? So this term here, expectation of x bar, is just mu. So this is just going to be mu squared. So the expectation associated with x bar squared is just sigma squared over n plus mu squared. So we can kind of finish through the rest of the derivation. So this part is just going to be simply, let's write it down here. 1 over n minus 1 times n sigma squared plus n mu squared minus n times sigma squared over n plus mu squared. And let's close the parentheses. And when we combine like terms and simplify, you'll have 1 over n minus 1 times n sigma squared plus n mu squared minus sigma squared minus n mu squared. But what happens? The n mu squared terms here cancel out, and this is just going to be 1 over n minus 1 times n sigma squared minus sigma squared. And you'll see that this term here is just, this will be equal to 1 over n minus 1 times n minus 1 times sigma squared. So this cancels out, and bam, you got sigma squared. So that's good. You have proven that this formula for the sample variance is indeed sigma squared in the expectation. So you have shown that the sample variance is an unbiased estimator. And a question you might be having is, why is there an n minus 1 in the formula? So intuitively, you might think that a sample variance is just simply the average spread. So you take the sum of the spread and divide by n, just like you do for arithmetic mean, right? Or the sample mean. Well, if you look at the derivation and go through this, right? This 1 over n minus 1 replaced with n means that you'll have an n down here, right? And it's going to get carried all the way through, right? This 1 over n minus 1 is going to become a 1 over n. And you'll see here at the end, right? You will see a 1 over n multiplied by an n minus 1. So you'll have a 1 over n times n minus 1 times sigma squared. And that's not going to be equal to sigma squared. So we add this n minus 1 in the denominator of the sample variance formula in order to make our sample variance an unbiased estimator. So that's the reason why there is an n minus 1 in the formula for the sample variance. So hopefully you have enjoyed this video, and hopefully the step-by-step derivation gives you a good understanding as to why the sample variance is an unbiased estimator. Tune in next time for another video in the probability and statistics playlist. Have a good rest of your evening.